Hello everyone, my name is Hritvik Taneja. Today I'm going to talk about our paper, Hot Pixels, Frequency, Power and Temperature Attacks on GPUs and ARM SoCs. This work wouldn't have been possible without our collaborators at Georgia Tech, University of Michigan, and Ruhr University Bochum. Let's start by talking about evolution of side channel attacks. Side channel attacks started with exploiting physical side channels. These side channels exploit physical properties such as power consumption and EM radiations. These require specialized hardware such as oscilloscopes and EM probes. The advantages of these kinds of attacks are that they are difficult to mitigate because they exploit inherent physical properties, and this is the reason why they also work across different microarchitectures and even different generations of devices, because physical properties are hard to change via microarchitecture design. So as technology progressed, we saw the emergence of microarchitectural side channels. Here, instead of relying on external hardware, we saw leakage via software visible APIs. The advantages of these kinds of attack were that we didn't require any physical proximity to the device because we didn't require any specialized hardware, so we could mount these attacks remotely. There's a third class of attacks which are called hybrid side channel attacks. Here we get the best of both worlds, where we get to exploit the physical properties of the system, and we can also mount these attacks remotely. So how do we go about this? For hybrid side channels, we measure physical properties via internal sensors. How do we measure that? Operating systems usually provide APIs to measure these physical properties. So the advantages of these kinds of attack are obvious. We can mount these attacks remotely. And just like physical side channels, these attacks are also difficult to mitigate because they rely on inherent physical properties, and they usually work across different microarchitectures and even across different device generations. In this work, we show that hybrid side channel attacks are present everywhere. They're present on desktops, they're present on laptops, they're present on mobile phones, and even on GPUs. We use the leakage from we exploit the leakage from hybrid side channels via unprivileged native users and even from browsers such as Chrome and Safari. So here's a sneak peek of our work. We show that CPUs and GPUs try to maintain a three-way trade-off between frequency, power, and temperature. This image of three cute dogs trying to eat from the same bowl depicts this trade-off. While trying to maintain a balance between frequency, power, and temperature, we see that these devices leak via two physical properties when one of them is an operational constraint. So for example, if power is an operational constraint, let's say a CPU has a power limit set up, we see that we see data-dependent behavior in frequency and temperature. Now we use this behavior to mount pixel stealing, history sniffing, and website fingerprinting attacks across Chrome and Safari. So how do we go about this? Before talking about side channel and attacks, let me first talk about machine cooling. So the more transistors we put on a chip, the hotter it runs, which is why we need big heat sinks to cool the CPUs down. But these heat sinks will make our laptops big and bulky, which we don't like. We like thin laptops these days. So what do these laptops do? They install really small heat sinks, which don't usually have the heat dissipation capacity to cool the CPU down when it's running at its maximum utilization. So what do these CPUs do in order to prevent themselves from burning to the ground? They implement something called DVFS. DVFS allows these CPUs to adhere to certain power and thermal limits so that they don't burn themselves to the ground. Now, we have this really nice, cute, beautiful idea of DVFS, and I dedicated an entire slide talking about it. So does this idea have any security consequences? In order to understand that, we perform an experiment where we run these two workloads. In the first workload, we increment a variable by 1 in an infinite loop, whereas in the second workload, we increment the variable by 0. Here are the results of these experiments on an M1 MacBook Air. We see that the temperature of the CPU remains constant when running both these workloads. Orange depicts when we are running the workload with data equal to 1, and blue depicts when we are running the workload with data equal to 0. So we see that the temperature is constant, but frequency and power are vastly different and also leak information about the data being processed. Now, the next plot is from an M1 MacBook Pro, and we see that the plot looks different, even though they have the same chip. Plot is not the only different thing on M1 MacBook Pro. We also paid $300 more to make this plot. Why did we do that? Apple went ahead and bought a $300 fan. What did this achieve? It made sure that the CPU ran at its maximum frequency because the fan provided the chip with sufficient cooling. So we see that frequency for the M1 MacBook Pro when running both these experiments is limited by its maximum operable frequency, which is 3.2 gigahertz, but we still see leakage via temperature and power. Now, because the M1 MacBook Pro struggles to maintain temperature, we classify it as being thermally constrained, which means that the CPU will not leak any information about the data being processed via temperature, but it will leak information about data being processed via frequency and power. Similarly, we classify M1 MacBook Pro as being frequency constrained, which means that the frequency remains constant, but the temperature and power leak information about the data being processed. This is the three-way trade-off that I was talking about before. So CPUs are not the only device that compute on secret data. We have GPUs. What about them? GPUs have thousands of cores. They run hot, and they have massive cooling fans and a lot of memes. So are these massive cooling fans enough to cool them? You guys might have guessed it. No, they're not. What do GPUs do? They implement something called DVFS. So here are the results of certain experiments on an M1 MacBook Pro and an AMD Radeon RX 6600 discrete GPU. We see that, so the experiment is that we compute on white and black pixels and render them on the screen. And we measure the time it takes to render these pixels, and here are the results of those experiments. We see that the white pixels take a lot of time to render, whereas the black pixels comparatively render quickly. So, and this timing is directly proportional to the frequency of the GPU. Now we have this nice timing difference between white and black pixels. What do we do with this? Pixel stealing attacks. Before talking about pixel stealing attacks, we need to first understand what SVG filters are. So SVG filters can turn this normal looking gmail.com web page from this to this. So for this particular transformation, we use the FE Gaussian blur filter. SVG filters can be used to produce various effects. We saw the blurring effect that the FE Gaussian blur filter can produce. The FE color matrix can produce the color saturation effect, which we see here. Now, these filters can be applied to almost any HTML element in the DOM. It can be applied to a div or to an iframe. So we use these SVG filters to compute on pixels across security boundaries. Next, the other properties of these SVG filters is that they are stackable, which means that we can stack these filters on top of each other until the GPU catches fire, or in our case, just throttles. So now I'm going to give a brief overview of the pixel stealing attack. So let's say we have attacker.com, which embeds an iframe with a source victim.com. Now, I would love to read the values of the pixels inside this iframe, but Chrome would not allow me to do that. So, but I want to do that. How do I read these pixel values? So I isolate a single pixel and inflate it to the entire screen. I use a bunch of CSS tricks to do that. Next, I apply a bunch of SVG filters, which have two outputs. One is the resulting image, which is a blurry looking image that we see here. The other one is a throttling GPU. Now, depending on whether the filter application takes longer or shorter, we can classify the target pixel as being black or white. Now, here are the results of these experiments on various devices. These attacks works on a bunch of M1 and M2 MacBook Air, Pixel 6 Pro, OnePlus 10 Pro, and NVIDIA and AMD discrete GPUs. The average time to steal a pixel is around 10 to 20 seconds, and the accuracy is around 60 to 80%. Now, the next most popular browser after Chrome is Safari. What about Safari? Safari does not serve cookies across iframe. What does this mean? This means, let's say we open an iframe inside Chrome. Chrome will serve the cookie to this embedded iframe. What does this mean? This means that Chrome knows about my personal information. So when this embedded iframe is opened, I'll see a personalized message such as welcome Hritvik. Now, when I do the same thing in Safari, because Safari wouldn't serve the cookies to the embedded iframe, I'll see something like welcome new user, which is a generic text. Now, this acts as a countermeasure to pixel stealing because Safari doesn't know any of my personal information and everything it'll show will be public. So we can't steal what's already public, right? So can we steal something else? The fact that I'm standing here means we can steal users' browsing history. This is also a target of interest. Browser vendors will not allow you to read the color of the embedded link. But we want to know this. But we want to know if the user has visited youtube.com or apple.com. How do we do this? Attacker.com embeds multiple links. Then we perform pixel stealing attack on top of this. And based on the timing, whether it's fast or slow, we can classify whether the link is visited or not. Now, this attack works on the M1 and M2 MacBook Air and iPhone 12 with 13. The average time to recover whether a link is visited or not is around 200 to 250 seconds, and the accuracy is around 90 to 100%. Now, our last attack is a website fingerprinting attack. How do we go about that? So macOS provides APIs to measure GPU frequency and power. These APIs are accessible by unprivileged users. This is a huge security problem because any random person can now read your frequency and power when you're computing on GPU. Which also means we can read your GPU frequency and power while you're browsing the internet. To show how we can exploit that, we mount a website fingerprinting attack. Here we see traces of GPU frequency and power from 3 websites: Google.com, Amazon.com, and NewYorkTimes.com. We see that the frequency and power of all these websites are different, and it turns out it's also fingerprintable. So on our proof of concept attack with a corpus of 100 websites, we see that we can guess the correct website 27% of the time, where the baseline is 1%. This brings me to the end of my talk. Here's a summary of our work. We show that there's a 3-way trade-off between frequency, power, and temperature, where we see leakage via 2 physical properties when one of them is an operational constraint. We show data-dependent behavior of CPU and GPU. We use this data-dependent behavior to attack, to mount attack across multiple devices, and namely pixel stealing, history sniffing, and website fingerprinting. Thank you guys for listening, and now I'll take questions.